Welcome to module 2. So now we are finally going into the details of quantum information science. So we'll start with what is a quantum bit, what is superposition, how is it different from a classical bit, how do we measure these bits, and how do we represent them. So let's start. Hope you remember from our previous lecture that we took the example of coins to represent classical bits. We presented heads as 0 and tails as 1. Now we can consider this example again for considering qubits, but here is a remark. So when you toss a coin, we know for sure that it will either land heads or tails. Now, of course, we are assuming that it will land, it won't just stay standing like this. Okay. It cannot stay anywhere in between. So it is either 0 or 1. However, here's how a qubit differs. It can be 0 and 1 at the same time. But what it means actually is that it is in a superposition of 0 and 1. It has not yet collapsed into one of these states. So if you toss a coin and see it in the air, it can be somewhere in this position, or in this position. All these states are the superpositions of the head or the tail. This is not very clear yet because the coin is not the best example. So let's look at a different example. So we will look at an example of a compass needle. So if you take the compass needle, let's say this is our compass needle, it will always align according to the magnetic north and south pole of the earth, right? So this is a screenshot from my phone, and when I rotated my phone from 90 degrees, it went like this. So this is our magnetic needle, and if I place it at 45 degrees, so this is our magnetic needle. So you see, it is always aligning to the embedded magnetic field of the earth. Let's say the magnetic field of the earth is something like this, right? It is always aligning to this. So when I twisted my phone, the field became like this. So this is a better example to define a qubit. It always, when we collapse it or measure it, is in the north-south direction according to the applied magnetic field. However, if we now forget the magnetic field of the earth, let's say there's no magnetic field and the compass is free to rotate, it can be in any of these directions, right? It can be in any of these directions. It is only when we try to measure it, and how we measure it, we turn on the earth's magnetic field when it aligns according to these north-south positions, here or here or here. So this is a much better example of superposition. Now, it is an example, and at the same time, this is how actually qubits work. So if you've heard, like, I'm pretty sure you've heard of quantum computers, we talk about electron spins. So you see the electron spin. This is our applied magnetic field here. This is our applied magnetic field. And the qubits or the electron spin will align according to this magnetic field. Now if we turn this magnetic field off, let's try to turn this magnetic field. Let's see. So let's say this is off now. If we turn this magnetic field off, now the electron is free to be anywhere. And this, now it is in a superposition. It is now in a superposition of these states. Now you might wonder, it is all dependent on how we measure. So I can also say that when there is no external magnetic field, the electron is in the superposition of these two states. So earlier we considered, just to clarify, that our electron is in a superposition of these two states. Okay, let's name them 0 and 1. But I can also say, when I do not know where how my electron is, it is in a superposition of these two states 0 dash and 1 dash. And yes, this is exactly what happens. So it is the experimenter or the observer who determines how the qubit is in a superposition, or of what states the qubit is in a superposition, and we call these states the basis states. So the basis states are nothing but the states in which we choose to measure the qubit. So if I choose to measure the qubits in these states, my qubit is in a superposition of 0 and 1. If I choose to measure the qubit in these states, my qubit is in a superposition of 0 dash and 1 dash. And now I want to measure the qubits. I want to measure the electron spin. I will simply turn on my magnetic field again. So I turn on my magnetic field back again, and now it will align either here my magnetic field is aligned like this, so my electron will collapse either to this state or to this state. If my magnetic field were to align like this, so let's say this is north, this is south, then my electrons would collapse into these states. I hope this explanation made it much clearer. And this is very important because we know that quantum mechanics inculcates the effect of observer into the system. And this is how the observer plays a role. It chooses the basis in which the electron or the qubit would collapse. So let's move further and consider. So now we represent a qubit using a Bloch sphere. Now this looks complicated, but you just assume it to be as the latitudes and longitudes of our Earth, right? So if we want to pinpoint a location, we specify the latitude, let's say 36 north and 73 east, and we can pinpoint where a person is standing or where the thing is. Now remember that anything can only be on the surface and nowhere else. So it's a hollow sphere. It's not a solid sphere, so you can't be inside. You have to be on the outside of the sphere. And what this means is that the magnitude is always 1. Now we will get into this later. What does it mean by magnitude 1? But it is a concept related to normalization. Just to give it a bit more of a context, I hope you're familiar with the Dirac notation, and where we present our qubit with this. Let's say 0 plus 1. Let's attach these coefficients alpha and beta. So what this means is the probability of measuring the state, probability of measuring a state, of measuring our qubit psi in any particular states, let's say psi 0, is always 1, which means the magnitude or the radius of this sphere is always 1. Okay. So for now we can forget about this, and we'll focus on the actual mapping. Okay. So if you see on this Bloch sphere, you can instantaneously spot this 0, this 1, this x, and this y. Okay. So here's how our convention is. This is the z-axis. So 0 and 1 is our z-axis. This is our y-axis. Okay. And these states I will describe later. And x-axis points out of the page. Okay. This is the classical convention in the Bloch sphere map. So now the electron spin, again we'll jump back to our example. The electron spin can point in any of this 360 degrees, or like anywhere on the Bloch sphere. I hope you can imagine how the electron can spin anywhere around. Now it is the observer's choice whether he wants to measure it along the z-axis or the x-axis or the y-axis. The z-axis, the x-axis, or the y-axis. It is totally up to the observer. And so what does the observer do to measure the electron? It turns on the magnetic field, and the electron will collapse accordingly. So let's say if he turns on the magnetic field in the z-axis, the electron will either collapse to 0 or 1. So 0 and 1 are just a notation. So if we just go back to our example, this is the Dirac notation, we would name this state as 0 and name this state as 1. Right, so this is our 0 state, this is our 1 state, and this is the axis. Now if we want to measure the same qubit in the, let's say, x-axis, so now we would not follow this, now we would not name our states 0 and 1, because then it would become confusing. We won't know if we are measuring it in the z-axis or the x-axis. So we name these plus and minus. We will get into more details in this lecture later, but you can just remember now when we change our basis of measurement, we change our states in which the qubit would collapse to. All right. This is just a kind of summarizing slide. These are our states 0 and 1. We can expect them as a coin, but we discussed coin is not a good example. So you consider the magnetic compass or the electron spin, which is actually used, and we can name the states 0 and 1 if they're aligned according to the z-axis. So here 0 and 1, you see the z-axis. If they're aligned according to the x-axis, let's say it would be something like this. We can name these states plus and minus, and if we want to have them along the y-axis, we can name these states iota and minus iota. Now we will get into the details later how this are iota, minus iota, plus and minus, but these are just naming conventions. You don't need to worry about it. Now for simplicity in this lecture, mostly we would consider our z-axis as the axis along which we want to take the measurement. So our basis states will be 0 and 1. Okay. So this is an example of a superposition. What it means is that our qubit, let's name it q, is in the superposition of the states 0 and 1. Don't worry about this 1 by root 2, we'll come to that later. But if you've this concept has been discussed in the lecture of Dirac notation, and so we can break it down as 0 plus 1. Now you see the magnitudes of both of these are equal, right? So this state is somewhere in between this state is somewhere in between this 1 and 0. Okay, so, and we know it has to be on the surface, so we can quickly point out that this has to be on the equator, because that's the only region where both 1 and 0 exist in equal components, right? And we further find out, which we'll again discuss later, that this thing turns out to be this point, plus. Okay, and we will come back to it, like how is it exactly done in this module later, but this is the crust of it. This is how the superposition works. It's in between this 1 and this 0. These are a few more important superposition states. So we had 0 plus 1 here. We simply replace this plus by minus, and now we again know that it has to be somewhere on the equator. This time it turns out to be at the back, and this state is called the minus state. Here we take a similar thing, but this time it is we have our coefficient as iota, and again this is just a representation, spherical coordinates, we'll get to it. Again it has to be on the equator, and it turns out to be on the plus y, which is called the state iota. Similarly, this state is called the minus iota. Now we name these states. So let's get back to a minute. We know that our basis state is our basis is the z-axis, and so this is all we care about. So you see all these states are represented as 0 and 1. However, certain points are important on the Bloch sphere. So we looked at some special states until now, on all the corners. So you see these are the important states. This is the basis of measurement, 0 and 1, and then these are some more important states, plus and minus, minus iota and minus iota. Now let's discuss here for some more time. If we were to choose our basis of measurement as, instead of the z-axis, I choose the x-axis. So now all my states would be represented as plus and minus in the superposition of these. So for example, let's say I consider this superposition plus minus. So this would become plus 1 by root 2 plus 1 by root 2 minus. Now again, this is in the exactly the middle, so we know the state would somewhere be here. Okay, so again, this is a superposition, so all the basis states have superposition. These are the few important ones. Now we consider more states. We considered the important states in the earlier slides. So for example, this state, it is located right here. Now we'll get to it how it is located, but this is just an example. So you see, this can be broken down like this: 1 by root 2, 0 plus e iota pi by 6 by root 2 and 1. And when we map this state, which we'll describe in the next slide, we get the state to be here. So as you see, we are dealing with complex numbers here, and all the Bloch sphere mapping is done using polar coordinates. So it's important to know the polar and the spherical coordinates, and I'll also try to give a short review. These are a few more example states. Root 3 by 2 plus 1 by 2, 1 state, and we'll learn the mapping, how are these states mapped, for which we need complex numbers. So here's a quick review of the complex numbers. I hope you are all quite familiar. We present a complex number z as x plus iota y, where this is the real component and this is the complex component. This is our, similar to Cartesian plane. We represent the real numbers on the x-axis and imaginary numbers on the y-axis, and this is quite trivial. This thing, the real component becomes x cos theta, and the imaginary component is r sin theta. This is how it is represented in the polar form. So this is the polar form and this is the Cartesian form. By Cartesian form, we have x and y, so we find the x, and let's say we find the y, and we get this point. This is the polar form. Why? Because we want to represent it on a Bloch sphere. So we take the radius, which we described earlier, always has to be 1. So we take the radius, let's say here, and then we track using this angle theta where our point is on this sphere. Okay, this is just how we calculate the magnitude, the radius, x squared plus y squared, and this is how we calculate the theta. These are quite trivial formulas. All this is done now using this identity. This is called Euler's identity, Euler's form, or Euler's identity. We can represent, let's say, this is the conversion from polar to Cartesian, which is also very important. We can easily see like e iota theta is cos theta plus I sin theta. So you get r cos theta plus iota sin theta. When we broke it down, we get x plus y, and this becomes x plus iota y. We are back to our starting point. This is just the calculation of the magnitude, how we obtain r. Here are some more concepts for complex numbers that you should know. The complex conjugate, I won't go over these in the details, you can just have a look. Anyway, so now measurement in the z basis. So now we actually start playing with the bits. Now we start manipulating them and all that. So let's say we have this piece 1 by root 2, 0 plus e iota pi by 6, 1. So let's open it up a bit. 1 by root 2, 0 plus e iota pi by 6 by root 2. So this all comes from the Dirac notation, and you can go watch the lecture for the Dirac notation available. We break down this, and what do we mean by measurement? So we know quantum mechanics is probabilistic. So what we do is, this is our state psi, and we try to calculate the probability of finding psi when we measure it in either 0 or 1, because we have our z basis. So that's what we find the probability of. And how do we find the probability? Let's say psi is equals to alpha 0 plus beta 1. We take these amplitudes and square them, alpha square, beta square. So these give us the probability of the qubit being in 0 or 1 when we measure it. So for this particular state, we have this thing 1 by root 2. We obtain 1 by root 2 square is equals to 1 by 2. So the probability, when we measure the qubit, the probability of measuring the qubit in the state 0 is half. And similarly, this is also 1/2. So it's 50-50. Here we see another example. Here we have alpha is equals to 2 by 3 and beta is equals to 1 minus 2 iota by 3. So their probability will be alpha square and beta square, which is calculated as here follows, and we obtain the probability of 4 by 9 and 5 by 9. Here we talk about normalization. So we discussed how in the Bloch sphere everything has to be of equal radius. So that is because if you remember, the probability always lies between 0 and 1 of anything, and if it's in the total probability must always be equals to 1. So if we define our wave function in all space, something like that, and we measure it, we know that a qubit has to be somewhere. So the probability can't be less than 1. It can never be less than 1. It has to be somewhere. We will find a particle somewhere in the whole space. So when we integrate it over whole space, let's say we are dz or dr, because we are integrating in the whole space minus infinity to infinity, this is how we represent the probability, and this has to be 1. This is how anything is normalized, but this is the complex integration. We don't need to get into this. Okay, here's the important part. Here's our state. Psi is equals to root 2 0 plus iota 1. Now this is not normalized. What we mean by normalization, as we looked earlier, this is alpha square is equals to 2 and this is beta square. And now if we consider the total probability, which is alpha square plus beta square, which is 2 plus 1 equals to 3, but we know it should be 1. So we try to normalize it. So we add this normalization factor a and we multiply it as follows. So now our state is a root 2 0 plus a iota 1. So this is our alpha and this is our beta, and we go. So we square alpha, this is alpha square, this is beta square, and we obtain this 3a square. Now we know that 3a square should be equals to 1. So we can get the value of here 1 by root 3. A square is 1 by 3 and a is equals to 1 by root 3, which we can see here. Okay. And so now our final states after multiplying it with a becomes this. And just to check the back examples, you see the total probability here, if we add them, equals to 1. The total probability here, half plus half equals to 1. So these states are normalized. Okay. So this is just normalization. So here's our state, root 3 by 2 0 plus 1 by 2 1. It is represented like this on the Bloch sphere. From here we obtain our theta and phi and simply plot this state like this. So now you see this is in the z basis. If I choose to plot it in x basis, right, so I would represent my psi as something, let's say alpha plus and beta minus. And when I try to plot it, I will get the same point again, because the state doesn't care which basis I'm plotting it in. It will still be at the same position on the Bloch sphere. So now we will try to measure this bit in across 4 different bases. So our first basis will be simply the z basis. So we simply take this alpha, take this beta, alpha square is equals to 3 by 2 or 3 by 4, beta square is equals to 1 by 4. This gives us 75% and this gives us 25% probability. Now let's check the x basis. So to convert any basis, to measure it in any basis, first we need the state in that particular basis. So we try to do that. We know the conversion from 0 to plus and minus and 1 to plus and minus. So we convert our state from the z basis to the x basis. And then we can simply take the amplitudes alpha and beta and we obtain these values. Simple. And now you see the probability here, it's 0.93, well, 93% for plus state and 7% from minus state. And this is quite evident from here as well. If you see, this is quite near the plus state more than the minus state. So this is right here. So it's easier for it to just be here than here. Okay. So this is quite evident. And in the y basis, we repeat the same process. We represent 0 and 1 in the y basis and get the overall state in the y basis and measure the probability half and half, 50%. Now we know that if it is 50%, it is somewhere on this axis, and which is true. It is exactly here. It's on this plane. So if we were to take the north and the south pole as this on the y-axis, this would be our equator. So it's exactly on the equator as we expected. Okay. Now let's take a completely different basis, like completely arbitrary. So we take this basis. This is a random basis. We represent this basis in the z basis because that's our convention. But so this is our new basis, and again we do the same process. We write 0 and 1. So these are our two basis vectors, a and b. This one is a, and this one is b. Okay. So we write the basis vector in terms of 0 and 1, and we plug that into our original state. So we obtain our state psi in the new basis vectors a and b, and now we can simply measure the probability. So it is 5 by 8 present as fraction to be collapsed into this, and 3 by 8 into this. Now one more thing about measurement is the measurement collapses the state. So if it's we know that this quantum state is in a superposition, meaning that it is something like, let's consider a very simple example. It's 0 plus 1 by root 2 1. So it is in a superposition, but as soon as we measure it, it collapses to either 0 or 1, because that's the basis, again the basis that we are measuring in. So it collapses to 0. Let's say it collapses to 0, and now no more it is in a superposition. So what is since it has collapsed, when we measure it again, we will find it again to be in the state 0 because it has collapsed. Okay. So this is all. Next we will look at global and relative phases. So let's say the qubit from the last section, and we apply this global phase here and we try to measure it. So first we try to measure it in the z basis, and we get the same answers, 3 by 4 and 1 by 4, the same as last time here, 3 by 4 and 1 by 4. So this clearly didn't make any change. We did the same process. We took alpha square, so our alpha would become e iota theta root 3 by 2, and our beta would be e iota theta 1 by 2. And when we take square, because this is a complex conjugate, we would write it as e iota theta root 3 by 2 times e minus iota theta root 3 by 2. This would just cancel out and we will get the same thing. Similarly, we tried to measure it in our x basis, and we again got the same results as the last time here. So this clearly doesn't do anything to the state. The global phase doesn't do anything. However, you must remember that the global phase is irrelevant, but not the relative phase. What it means by relative phase is, for example, this is our plus state, 1 by root 2, 0 plus 1, okay, and we say we have iota, which is 1 by root 2, 0 plus iota 1, which can be represented as 1 by root 2, 0 plus iota 1, iota pi by 2 and 1. So this is a relative phase between 0 and 1. We cannot disregard this at all, because this changes the meaning completely. With the relative phase only, the state is I. If we remove the relative phase, it will become plus. So this is very important. So these two states correspond to different points on the Bloch sphere, and they can be distinguished by measurements in appropriate basis. So we can measure this in the x basis and this in the y basis. However, if we try to measure it in the z basis, this doesn't change anything, and that typically becomes, we still have a 50-50 probability. Now we finally come to how do we map these states. So this is the diagram that you need to keep in mind. This is how we represent our states, Dirac notation, and we convert it to spherical coordinates so that we can plot it on this Bloch sphere here. Here are the conversion. Alpha goes to cos theta by 2 and beta goes to e iota fine sine theta by 2. You don't need to get into the details how we derive these states, but if you want to, you can consider, or you can look up spherical coordinates and easily see the conversions. But you don't need to get into the details of it for the purpose of this course. Alpha is cos theta by 2, beta is e raised to the power iota phi sine theta by 2. And once we obtain these values, we can easily plot this, because remember, in spherical coordinates, all we need is our r, theta and phi, and we can plot it. We already know what our r is. It's always 1, not because our state is normalized. We can obtain our theta from here and our phi from here. We'll look into an example. So our final state psi becomes cos theta by 2, 0 plus e iota phi sine theta by 2, 1. And we can easily plot it using this theta and phi. Here's an example. We start with this state. This is the Cartesian, and we first convert it into polar coordinates. So we know we need r, which is x square plus y square, and we need theta, which is tan inverse y by x. So our x is 3 by 4, our y is root 3 by 4, so our r square is 3 by 4 square plus root 3 by 4 square, and you can easily see this is root 3 by 2 square, so our r is root 3 by 2. Now for theta, we have y over x, so our y is root 3 by 4 and our x is 3 by 4. We get 1 by root 3, which is and when we take the tan inverse of this 1 by root 3, we'll get pi by 6. Okay, so this is just simple. Now we'll move further. So we have converted this into this form now. From a notation, we know that we need this exponential with the 1. We can also keep it with the 0, but for notation we follow this convention and we want it with the 1. So for now it is with the 0, but we want it with the 1. So we multiply it with the global phase of e iota pi by 6, and we already saw how the global phase doesn't affect the state of the qubit at all. So we multiply it and we obtain this. Now this looks not very good. We don't like minus, so we multiply the state with e iota pi, which is basically nothing but 1. and we obtain this nicer looking with the plus thing. Okay, now we can use this to convert to have this in this form, and when we see, we get our cos theta by 2, which we needed of plotting. We get our e iota pi, e iota phi, and we get our sine theta. So we can easily represent our state as this. And what were the three components we need for plotting? R, theta, and phi. We have R equals to 1, normalization. We can easily obtain theta from here, and we can easily obtain phi from here. So let's see that. We clearly see phi is equals to 5 pi by 6. Sine, we know sine theta by 2 is equals to half, which means that, let's see here, theta by 2 is equals to 30 degrees, or theta is equals to 60 degrees, which is equals to pi by 3. And then we can easily plot that. So when we go here, let's see, we know our theta is pi by 3, right? And from this, so we go pi by 3 from here. And what was our phi? Our phi was 5 pi by 6 from this x-axis, and we rotate this 5 pi by 6 until here, right? And when we plot this from the center, we get our point here easily with theta and pi by 6, and you can see that here, it's right here. Okay, this is the end of our lecture for quantum bits, and here are some exercises. Just let me mark these for your ease. This is question number 1, you have to draw the Bloch sphere. Question number 2 is kind of a review for the complex numbers. Question number 3 is measurement. Question number 4 is sketching, and 5 is sketching, because the sketching is really important to know. Okay, see you in the next lecture, and if you have any questions, you can contact me in the office hours.